Hi, everyone. Today we're going to talk about our first law, which is new, called the Law of Detachment, and it's illustrated here in the Do Now. Suppose I had a conditional that was true. Okay, so suppose these two statements are true. And the first statement is, if Professor Plum was seen at Al's pharmacy, then he is guilty. So that conditional is true. Remember, this does not mean that Professor Plum was seen at Al's pharmacy. It means that if he was seen at the pharmacy, then he is guilty. But suppose the detective learns that Professor Plum was seen at Al's pharmacy. Then what would be his conclusion? Well, the conclusion would be that Professor Plum was guilty. So I'll write this down. Conclusion. Professor Plum is guilty. And this demonstrates the law of detachment. So let's put this information into logical symbols. Let P represent Professor Plum was seen at Al's pharmacy. And let Q represent that Professor Plum is guilty. So the original information can be written as follows. If P, then Q, in fact, I'll do this in black. If P, then Q would translate this conditional up here. And we have P. And that translates the second conditional, the second sentence, I should say. So if these two are true at the same time, then it follows that Professor Plum is guilty. So we're saying that if the conditional is true, and its antecedent is true, then its consequent must be true. And if you think about all the situations where a conditional is true, I mean, we could argue this. A conditional is true when we have if true, then true. When we have if false, then false. And if we have if false, then true. And note that if we had if true, then false, the conditional would be false. So if the conditional is true, okay, so this is when it's true, and its antecedent is true at the same time, then the consequent must be true. So it makes sense. And in fact, we can prove this to be a tautology. And I believe you did this on the homework, but let's rewrite it very quickly. So we're going to show that this compound statement is a tautology. Okay, now let's do that quickly just to refresh your memories. So note that I filled in the beginning part of the table. And notice that when we combine the conditional with the antecedent, we have true and true is true, false and true is false, true and false is false, and true and false is false. And now when this becomes the antecedent, and we combine it with the consequent, so it's if the antecedent then the consequent, we have if true then true is true, if false then false is true, if false then true is true, and if false then false is true as well. This is indeed a tautology. So now we have proven this law of detachment. Okay, let's re-summarize it on the next page and discuss another way to write this. So I rewrote the law of detachment for you here again so I could refer to it. We proved it using the axioms for a conjunction and a conditional. And now whatever we prove we call a theorem. And in mathematics, a tautology is a compound statement which is true regardless of the truth values of the individual simple statements that it contains. And the conditionals that are tautologies can be made into theorems or laws. So this is a special law that we will be using in our logic proofs called the law of detachment. But a law can usually be written as a conditional. And the antecedent of this conditional is called the given. And the consequent of the conditional is called the conclusion. And when the antecedent is composed of a conjunction, we don't write the word and all the time. This is another way to write the law of detachment, a shorter way. And it looks like this. A shorter way to rewrite the law of detachment, which we will prefer from now on. And that is, we write the first part of the given in one line, so that's when a conditional is true, and the and is implied. So we don't have to write it. And underneath it, we write P. So if the conditional is true and P is true, the antecedent, then is implied with this horizontal line. And whatever goes below the horizontal line is the conclusion, which is Q. Some books write 3 dots, but I'm not going to do that. It's read therefore Q or then Q. So I will be doing this. Whatever goes above the line is the antecedent or the given, and whatever goes below the line is the consequence. Q. Okay. And this is another way to write the law of detachment. And again, we could have 3 things above the line. It's understood that and goes between each statement. So I'm going to write this down. Above the line, understood that each statement is combined with and. So now let's practice. For each following pairs of statements state what conclusion if any can be inferred. Okay, so let's take a look at this problem. I'm going to put a few up. Okay, so I'd like to practice the law of detachment with you. Let's take a look, say, at number 1. Well, number 1 is easy. It's just right above. We have a conditional that's true. P is true, so therefore we conclude Q. But if we take a look at number 4, here a conditional is true, but the consequent is true. Well, if the consequent is true, think about it. So if this is true, there are several ways we could make the conditional true if S is true. T could be false or T could be true. So that means there's no conclusion. And you could think of it logically, but the law of detachment says we've got a conditional, the first part is true, then the second part is true. All right, copy the others and try them by yourselves. Okay, so let's check the others. So in number 2, like in number 1, we can conclude not S by the law of detachment. And number 3, in the same way, M. Number 4, we already did. 5 is like number 4. There's no conclusion because the consequent is true. And number 6, because there is that implied word and a conjunction is commutative, it doesn't matter which one we state first, so we conclude S or T by the law of detachment. Okay, now let's look at another example. Okay, let's take a look at a logical argument in mathematics. We'll start with a very simple problem. Okay, suppose we were given the following information. If Bonnie goes to the dance, then she did not go canoeing. She did not go canoeing this weekend. And Bonnie went canoeing this weekend. So this word and is implied, even though we don't write it. And we want to prove that from the two givens, that Bonnie did not go to the dance. Okay, so the first step in mathematics is to write a key, but the key is written in the following way. We'll pick letters for each simple statement. So let B represent Bonnie goes to the dance. And let C represent that she goes canoeing. This weekend. And once we represent each simple statement, we translate the given using the proper connectives. So let's do that. Okay, so this is step 1. Step 2, given. If Bonnie goes to the dance, that's if B, then she does not go canoeing, so then not C. And if Bonnie went, and Bonnie went canoeing, and C. Okay, again, this word and is implied. And we want to prove that she did not go to the dance, so that's not B. All right. Now, one way to do this, okay, is to write one big compound statement and show it's a tautology. So I could summarize this as my antecedent and write if B, then not C, but I have to put parentheses, and C. So the given is the antecedent of my conditional. And what we want to prove is the consequent, not B. And we could show what we want to prove. So one way to do this is to show that this is a tautology, which would require a truth table, and that's very doable, actually. However, sometimes our arguments will involve many simple statements, like 4 simple statements, B, C, D, E, and an F, in which case our truth table would have many more rows. So this is not the most efficient way. Another way to do this is to write what we call a statement reason proof. So we have one column called statements and the other column called reasons. And for every statement, we write a reason, and we number our statements, and we number the corresponding reason. And whatever is placed in this statement column must be true. Okay? So it's understood that whatever goes in the statement column must be true. So let's start with the given, which is true. So we'll write, if B, then not C, that's given. That's the reason. And C, that's given. All right. Now, we only have one law called the Law of Detachment, but we have a little problem here. The Law of Detachment says that the antecedent has to be true and the conditional must be true. But C is not the antecedent of the conditional in step 1. How can we rewrite number 1 so that the C is in the front? Well, if you go back to the previous lesson, we talked about the law of the contrapositive. So we could write step 1 as the negation of C, if that, then not B. Okay, and the reason is the law of contrapositive and we identify the step where we're using it, step 1. Now we simplify this and we say, well, this is the same as if C, then not B. And that's called the law of double negation. And these were tautologies we proved at the very beginning. And that was used on step 3. Now, when we take a look at steps 2 and 4, we can use the law of detachment and say, well, if C then not B is true and C is true, then not B holds. And the reason? Law of detachment in steps 2 and 4, or 4 and 2. The order doesn't matter because, as we said, the conjunction is commutative. So this is a way to write out the proof using a statement reason format. And this is the format we use when we get to geometry. So we want to make sure that we're prepared for our geometry. And this is the format we will use from now on, except that we don't have too many laws, so we won't have too many proofs. But that's the idea. Okay, in this last problem, we've got 3 variables, S, T, and R, and sometimes in logical proofs, we are given the letters directly. So let's see how we could prove this using different laws that we've studied. So remember, we've got the law of double negation, we've got the law of the contrapositive, we've got the law of detachment, which is what we will prove because we do have a conditional here, so it makes sense. All right, so let's begin. So we begin by writing statements and reasons. And we could begin with the first given. That's given. And we could write the second given. And in fact, a lot of students just begin their proofs by writing the given. Okay, now if we were to use the law of detachment here, and we have R, we need an R in the beginning of this conditional. So we're going to take this conditional, and remember, we could always flip and negate by the law of the contrapositive. And we're not going to skip any steps here because in a proof, we have to include every single detail so the reader can follow. So this is the law of the contrapositive. And don't forget to write the line, step 1. Now, we're going to simplify this using the negation laws. This would give us R, and we do one at a time. This is the law of double negation. And we don't rush through the proofs. Every step must be included. And then we could rewrite this side. Recall, we've got DeMorgan's laws negating a disjunction, and we have this, where the disjunction becomes and we negate each disjunct, but this has to be put in parentheses. And we have DeMorgan's laws. On step 4, on the right side. Then, of course, we use the law of double negation again. And we have a choice. We could either write the same reason as 4, or we could say law of double negation, but we would have to change the step to step 5. Okay, and now, finally, we combine these two. We've got a conditional that's true and the antecedent true. And so we conclude S and not T. And this is the law of detachment. From steps 2 and 6. Okay, now there's something else we could conclude here if we went on. If we went on, we could also prove that S is true. And we could also say that not T is true. Can you think of a reason why both S and not T are both true? Well, again, whatever goes in the statements column must be true. And if a conjunction is true, then if a conjunction is true, then both of its conjuncts must be true. So we write here number 8. If a conjunction is true, then both conjuncts must be true. And this is the axiom for a conjunction. So that was from step 7. And number 9 is the same as 8 from step 7. And yes, some books call this the law of simplification because it's very easy to show that if P and Q is true, then P must be true. That's a tautology. And if P and Q is true, then Q is true is a tautology. So we could add this either as an axiom or the law of simplification. So let me write this down for you. The law of simplification. And once in a while, we need it when we want to isolate one of the simple statements. We can always isolate the simple statement when we show that the conjunction of that simple statement with something else is true. So we could write P and Q is true, then P. P and Q is true, then Q. And the words are here for the law of simplification. So, yeah, there's a little bit of a contradiction here because I called it a theorem because it is a tautology. It's an axiom. All right, there's a fine line between the two, but I'll let either one go. Okay, so we could call it the law of simplification. Or if you'd rather write out the axiom for conjunction, that's fine also. Okay, so that takes care of the introduction to logic proofs. And remember, we cannot skip steps. There is a step. Every time we simplify, we use a different line. Okay, everyone, have a wonderful day. Tomorrow we'll take a look at another law. Bye.